Hello, hi everyone. Before we begin this awesome talk, I have to make an uncomfortable announcement to you guys. So I've been told by the program office that several people who are coming from ISC and Bangalore are using the ICTS campus shuttle, which is meant for the ICTS staff. So in particular, the 8:40 a.m. shuttle is a small vehicle which is used by ICTS staff. And because of this, they are unable to board that shuttle and they have to wait for a long time. And as you can imagine, this program is successful because of those guys. I mean, I don't do much, they do most of the heavy lifting. So for interest of them and for sake of all of us and for you guys also, you are kindly requested to not board the 8:40 a.m. shuttle. There's a separate shuttle which is arranged for you guys. So please board that shuttle. And same goes for the return. So the 4 p.m. and the 5:15 p.m. shuttles are again for ICTS staff. For you guys, there's a separate shuttle, I think at 5:40 or something. So please use that shuttle. I think you've already been emailed this by the program office, but I thought maybe it's good to also say this once. And just to be very clear, the morning shuttle which you have to board is at 8:15 a.m. Okay, not 8:40, it's 8:15. And the evening shuttle which you have to board is 5:40 p.m. Okay, so 8:15 and 5:40. And please wake up earlier in the morning so you can board this earlier shuttle. Thanks.
Okay, so it's a pleasure to introduce another old friend, Sanjay Shakkottai. I met him when he was a student in Bangalore and I was a young faculty in ISC. Mainly because he was a campus kid. I mean, his father was a professor there, so I used to couldn't avoid meeting him, let's say. And okay, so after Bangalore University, he did a master's in ISC itself and did his PhD in the University of Illinois and has been in UT Austin forever. And in addition to a lot of excellent research he is doing, he has done one major contribution to India. Two of his ex-students are faculty, one being my colleague Sharyu Moharir and the other is Aditya Gopalan in IS. So let's welcome Sanjay.
Thank you very much. So today I'm going to be talking about image editing, image stylization in very high dimensions. And the way I want to structure this is in two parts. Today is going to be more a tutorial on posterior sampling. Much of it is not work from our group, but just broadly. And tomorrow we'll talk about state-of-the-art algorithms which we have been involved in. So first, before I get into sort of what posterior sampling is and all that, let's talk about sort of what the goal is to do in these kinds of systems. Okay, so here's an example. So I have this image, let me see, of this rose gold. Okay, I'll just run up and down. You see that the image of the rose gold thing, that melting gold style, and maybe you give a prompt, a guitar. In less than a minute, you'd like to generate that guitar image. Or another example where I give you this glowing mushroom, that's my style, and I give you that dog, just one image. And I want to compose these together to generate a dog. So I want the content, I want the style, and to do content style composition. So this is the image that's resulting. And these are the kinds, so all the images I'm going to show you here are sort of from things that my group has been involved in. This particular thing actually has been in collaboration with Google and has been productionized in Pixel. So if you're using Pixel phones, or also if the Imagine product, then you may actually see some of these things in practice. This is one example. This is sort of content style composition. You can talk about other types of problems, which is, let's see, single image based thing. So somebody drew this image and we give the prompt a house on a hill or something like that. Let me see what the prompt was. A house on a mountain, and we're able to generate this. Again, this is not with you just have a base generative model, but there's no fine tuning or any such thing. This is all test time. I give you one image at test time and you want to generate it by real time within less than a minute. And these are all at high res, meaning 1024 by 1024. So basically, you can think of these as vectors in 3 million dimensions. So that's basically what you would like to deal with. So these are, we can also talk about style synthesis, meaning I give you a pair of images, this rocket ship and this mushroom, and say, create a tiger which interpolates between these styles. And so these are all examples of what I mean by image stylization. So another class of problems we could be interested in is cartoonization, and which are different types of stylization problems. So this is, I'm going to talk about some of these kinds of methods as well tomorrow. The base question in any of this starts with inverse problems, meaning I'll give you this blurry image, and you want to denoise it to get a sharp image. This is a motion blurred thing. You can start denoising it. So these are examples of things we have done. Or freeform in painting, meaning somebody has scribbled across this particular image, and then you want to clean it up. You want to get rid of that. These are all inverse problems in the sense that you've got some measurements which are, image with some missing parts, and you want to sort of generate a proper image. I'll be more mathematical in a second about these things, but right now I want to talk about what is the final goal before we go back and start talking about what the formalism is and how you start developing algorithms. Other types of questions which are really interesting are text-based image editing. So you give the prompt a high-quality photo of a tiger face, and you want to convert it to a high-quality photo of a leopard face. First of all, this is not a high-quality picture of a tiger face. So it's a low quality. So that means the prompt is not aligned with quote-unquote what we think is what high quality means. Okay, so you need to sort of figure out that alignment problem. And then after that, you want to edit. So you want to do this kind of stuff. So this is an example of text-based image editing. These are the types of problems that we have been working on. And all these algorithms, everything I've talked about here are in collaboration with with the Pixel team, with the Imagine team, within Google and Google DeepMind. And so much of this has been actually productionized. And what I want to talk about is here today, sort of some of the what's going on, what are the problems we're trying to solve when we want to formalize these things. And then what are the approximations we need to make, because you're dealing with such high scale that computation is, to do anything in sort of less than a minute is very tricky. So what are the constraints? What are the approximations? And then the algorithms. So that's my roadmap. Today I'm not going to get to these. I just wanted to start with this. Today I wanted to start with just what is the mathematical formalism, what have people done in the space, and so on. So this is the applied side of it. Let me switch to the practice side, the pedagogy side of this. So I'm happy I'll share this afterwards, but what I did over the last few months is to write a set of 22 lecture notes, which sort of takes where does theory and practice meet in terms of diffusions. So it all starts from Gibbs and Metropolis Hastings and 1940s when the sampling algorithms were developed. In the 70s, then we went to the Langevin dynamics, which are essentially Markov chain-based samplers. So really what you ask then at that point is, does this converge? How fast does it converge? What's the invariant measure? Geometric error, is this exponentially fast? So you want to talk about geometric ergodicity and things like that. So that's sort of where I start. And then sort of move to a Markov process view of this through push forward. So there are, all of you, this really aimed to the graduate students here. So many of you would have seen Markov chains and Markov processes, but there's a nice way to think about this through functional analysis, which is Markov processes are just push through semi-group generators and push forward measures. If you look at it that way, there's some really nice connections with essential differential geometry to Bakri-Emery criterion and log-Sobolev inequality. So we'll talk about what kind of samplers sample fast independent of dimension. So if the connection between sampling and Markov processes, you consider a Markov process and you sample it after, you look at the terminal state or stop after a certain amount of time in practice and say, this is what I want. In the image case, the Markov chain is operating in 3 million dimensions, that's the state space. And it's evolving from the initial distribution, which is something easy to sample, maybe a Gaussian in 3 million dimensions. And you run the kernel and you stop after some time. So if you're mixing time, the time takes for it to get to the stationary distribution is really large, then you're essentially screwed, right? I mean, you want it to get there quickly. So mixing time is a super important thing to think about. So we'll talk about LSI in that, and then we'll get to sort of VAEs and GANs. So all this is assuming you know what the unnormalized density you want to sample from. In reality, all you have is data. So you want to start thinking about it through a variational perspective, which goes through VAEs, GANs, DDPMs, and ELBO. And these are all in continuous time. You want to go back to discrete time. So you want to start thinking about sort of different types of coupling arguments. There are very beautiful ways of thinking about it, including Wasserstein coupling, and most recently, sort of using IMMSE. For the information theorists here, there's a really beautiful connection to sort of show errors because of discretization. So, so that's what I go through, and then rectify, then flow models, posterior sampling, and sort of the latest is DLMs, diffusion language models. So this is sort of a set of lecture notes I've developed. And so what I'm going to do today is pick a couple of these and sort of talk through it, because I can't go through all of these. But I'm happy to share a Dropbox link with whoever. All this is written out. I'm happy to just share this link with anyone. Okay. So what I'm going to do today is sort of posterior sampling, and then if I have time, I want to go back to just the old stuff, Metropolis, Hastings, Gibbs, which many of the professors in this room would have taught in their classes, but maybe the graduate students don't remember or haven't seen it recently. So I'll go back to these things and let's talk through that and end with that. And then tomorrow, I will basically get to the image, how do these things actually apply, and what are the difficulties when you sort of scale these things up. Okay, so that's my plan. Okay, so this is, today I'm going to basically talk about posterior sampling. All right, so this is, none of this material is original from our group. I rely a lot on my students. My students usually know far more than me. Advait and Litu are the students who work with me, and they know infinitely more than me, and they've helped me with this stuff. So yeah, the other references, much of the material here is from this collection of papers. I'll be happy to share this PDF with the organizer just after this talk, and yeah, perfect. So what is the problem of posterior sampling? I presume most of you have sat to Dheeraj's talk last week when he talked about diffusions as a generative model, score-based generation. Okay? So in summary, what it is a black box. If you have a density function P star and you want to sample from it, diffusion is such a black box. You run this thing, and this after one call of this black box, it does multiple iterations inside, whatever number of steps, but at the end of it, it produces an image, right? That's what you have trained for. So here you should think of X as a vector of pixels. If you're talking about 1024 by 1024 pixels, and each one in 3 colors RGB, you're talking about 3 million dimensional vector. So that's what you're talking about here. Okay? So you want to sample with that, and so I'm not going to talk about the base diffusion model. Somebody has already trained this, and this box is available to you. The question then is, I want to solve conditional samplers, meaning I give you some side information on measurement Y, and I'm going to use the word measurements in a very, very sloppy and generalized sense. It could be some part of the image, it could be a blurry image, it could be a projection of this image, or it could be some text describing this image. Okay, I'm using this measurement very, very generally when I'm talking about this. The problem is then I want to sample from the conditional distribution P of X given Y. And why? So for concreteness, if you want to think about infilling problem, the infilling problem is there's an image, some part of it is deleted, and you're asked to imagine what would be inside in that part and fill it in. Okay, that's called the infilling problem. So then Y would be the measurements of the pixel you actually have, and what you want to sample is P of X given Y. Good. All right. So I showed you all these images, so I'm going to skip. Let's just get to the business. So there's one thing that happens a lot in this when people talk about sort of inverse problems, and then what I've talked about is posterior sampling, and these words are used interchangeably pretty much in these communities. So let me just sort of show a simple calculation, which is very well known, which say what's the connection between solving sort of inverse problems and sampling problems. Okay, so I'm given, so for concreteness, I'm going to assume a linear measurement model, meaning there is, well, I don't actually, forget the word linear. I have a measurement model of the following form. There's some operator A, which operates on this image X. Okay, so it's a function. So maybe this thing, if it's infilling, it just blocks out certain pixels. If it's blurring, it's some convolution operation that's going on. And there's some additive noise to it. And what you have access to is Y. Okay? And now, given this Y, I want to reconstruct the X. This is the classic inverse problem. These kinds of problems have been studied for hundreds of years. I'm going to talk about, so I'm not going to give you a survey of what people have thought about these things. I'm just going to talk about this in the context of diffusion-based generative models. So I have this, so this is my measure, this is my observation, and I want to reconstruct an X. So I'll put a loss function. Maybe a simple thing is just a squared loss, okay? Let's assume for now that I have access to the measurement operator, okay? So this function is available to me as a black box. Maybe it's, actually I'll even assume I have it as a differentiable black box, okay? So I can differentiate through it. So in which case, then I just do a squared loss and then minimize this. Usually, at least in the image case, if I've deleted 50 or 60% of the pixels, then it's clear that there are many, many possible solutions that are consistent with the measurement. Okay, so an example, let me see if I have that example here, the panda picture. Second. Sorry about that. Should have had this ready. Yeah, this is a good example of what I mean by many, many problems. Look at the inverse problem of that panda with something missing there. The generative model has filled this in here, but it easily could have been that it was holding a stick or something else. So there's no unique solution. And if you restrict yourself to not be images or natural images or whatever we think of, then you can see that there's all sorts of things. If you don't assume there's sort of continuity of image, color, and all that, you could put in all sorts of things there which could plausibly be good solutions. Okay, so you need to regularize in some manner. And so the usual way, if you're in optimization, is to put in some sort of a regularizing function G, and solve this regularized optimization problem, ADMM, or whatever your favorite method is, and go for it. Well, you could think of this as a sampling problem as well, in the following sense. So suppose I have access to the distribution of images. So P star of X is some density function over images. Now, just as an aside, in practice, even though images are pixels, vectors in 3 million dimensions, it is commonly believed that it lives in a much, much lower dimensional manifold, roughly on order of 12,000 dimensions, or even lower. Okay, at least the big generative models, latent space are order of 12,000. You can go much, the belief is actually much lower than that, but this is where the generative model, the latent space usually is. In any case, so P star of X is actually a density on a manifold. Okay, that's something we need to worry about, and this is really one of the reasons why sort of latent diffusion models are so powerful. But this is stuff which Dheeraj covered, I presume. So I'm just going to assume that I have access to this P star function. Okay, so I wanted to solve this optimization problem, right? Minimize this. Instead, let me give a sampling equivalent statement for this. Okay. Let me sample X according to some distribution Q star, and I want to minimize the following optimization problem. Minimize the loss function with X being a random variable sample from Q, such that Q is close to P star, the ground, as close to ground star, the ground truth distribution as possible. So that's my KL regularizer. And solve this optimization problem to get a Q star. And then I will sample from this Q star to get a solution. This is a sampling view of it. You note that if there was indeed a unique solution, and I didn't put this regularizer, this optimization problem will just collapse to a delta function on the true solution. So this is another way to sort of, in problems which are ill-posed, this is another way to regularize it. Okay? And if you do this, well, we can rewrite the loss function as L is, I can just write as e to the minus L log. I can just rewrite it that way. It's once I write it this way, and the KL is nothing but Q log Q by P. So I combine these two. If I combine this thing goes to the denominator. And so what I have is this Q star minimizes this ratio of Q divided by P star e to the minus L. And so if this were so I can always normalize this and get it No, it's a constant anyway. So even though this is an unnormalized thing, I can always normalize it and pull out the constant out of the optimization problem. And so the solution to this is that Q should be proportional to this. That's the optimal solution. So essentially, the point is that if you want to solve an inverse problem through sampling, what you really care about is a measurement loss tilted ground truth distribution. So you have a sampler. So the sampling inverse, the posterior sampling problem in many of the things we are talking about effectively is this. I have a black box that can give you samples from this, but I don't want solutions from this. I want solutions from that. Okay, and how do you go about building it? That's basically the question, and that's all I'm going to talk about today and tomorrow. So literature, there are broadly two ways people have thought about this problem. The first is something called training-based approaches, and the other are called training-free approaches. So roughly, training-based approaches means that I will train a new model for Q star. I will train an infilling model. I'll train a deblurring model. Okay, and I'll talk a little bit more about the detail of that. The other way, which is today actually the state of the art, and which is for at least for images, everything is test time optimization, training free, is I don't want to train anything except on the fly. I'll give you one sample of Y. I'll give you a black box that can sample from P star and ask you to generate a sample from Q star. So that is what is meant by test time optimization or posterior sampling or training free approaches. All these mean exactly the same thing, and these words are all used interchangeably in this community. So direct approach. Okay? So the obvious thing, I've given you many examples of Z is basically tag pairs of X comma Y. X is your image, Y is the measurement associated with it. And so I can think of a function, I can train a Q star of Z is P star of X given Y. That's the function I'm trying to learn. I will learn that. And since all of you know what I mean, you have seen all this about scores, that diffusion models require scores. So what you saw when in Dheeraj's thing last week was what you needed to learn was a score which was the annealed score, which is grad log PT of X. So PT is the ground truth density convolved with noise. So it's some noise. Think of this as the distribution of noisy images. Okay, and what you need is this function. And he talked basically, I guess, for 4 lectures last week to tell you how to learn this function. Okay. So what I need now instead is this, which is the conditional distribution given Y. So I can train a new function for doing this, or I can play around with this a little bit and rewrite it using Bayes' rule as the following. Right? I can write PT of X given Y is PT of Y given X times PT of X divided by PT of Y, just Bayes' rule. It's a log, so I'll decompose it. Then additively, and then I'm taking gradient. This thing has nothing, this gradient with respect to X. So this one, there's a gradient here term. There's a gradient with respect to X term. This is independent of X, so it's 0. So let's stare at these two terms. The second term here is what Dheeraj talked about last week. This is just this alone, if you run this, would give you, will essentially when you terminate, give you samples from P star of X. Okay, you run a dynamic as T goes to 0, the usual reverse process, and you're going to get images. What is this? This is saying, what does the density of the measurements look like if I give you noisy images? So the imaging system is all about if I give you clean images, I will tell you what Y is, and therefore I can figure out what the density of Y would look like. If it's an additive Gaussian model, then condition on X, it's just a mean shifted Gaussian. Okay, the mean being A of X, that in the linear model. But that's not what this is asking. This is saying I have blurry images and I want to figure out why. So there's no clean way of figuring this out. Okay? From a geometry perspective, you can think these scores are just vectors. Okay, this vector is, you should think about this as sort of roughly pointing toward the manifold of images. You are in the ambient space. There is some manifold of images somewhere. Okay, you're at this point and you want to hit that. So this vector is sort of pointing towards that. It's not quite true because this is annealed. So it's a noisy thing. So it's the image distribution has been pulled out of the manifold and spread into ambient space. So but I'm going to ignore that detail. This one is pointing towards measurements. So this is saying, I want to guide my current state to be consistent with the measurements I have. So there are two things that are happening, right? You want to be consistent with distribution of images, and you want to be consistent with the measurements. And going through this log and this code is essentially saying, I'm just modulating this vector field of the base vector field by something else, which is, if you're given a measurement, if I had this function, I just need to additively sort of modulate it all the time. And then and if I run a diffusion model with these two terms, then I'm going to satisfy both the measurements and give you valid images. Okay, so this is really the thing. How do we learn this? So the learning-based approaches could learn just this. There are training approaches which try to learn this. These are much lighter weight networks. These are much smaller. Okay, you've got the base generative model that understands images. All this needs to understand is sort of starting from noisy images and measurements, how things happen. So this can be done. That's one approach. The other approach is sort of given a bunch of measurements, I could try to incorporate this into this itself by some LoRa fine-tuning of the model and so on. Okay? So there are fine-tuning ways. These are all sort of training-based methods where I can guide the images to be consistent with the style of measurements you have. I'm not going to talk about that. So if you're interested in going down this road, there are some very nice papers, blogs, please do read them. What I want to switch to is training-free approaches. Okay? These approaches assume access only a block P star, okay? Or some variant of it, which is grad log PT of X, where PT is P star convolved with N0 sigma T, where sigma T is some appropriately chosen variance function. The goal is to generate samples from P star X given Y. Okay, so let's talk about some ways you could do this. Okay, and then I'll talk about what the problems with these ways are and what people are doing. How much time do I have left? Okay, I'm about halfway through. Okay, good. So the one method could be split Gibbs sampling. So I would like to cover Gibbs and Metropolis Hastings because I'm going to talk about Mala and stuff in a few minutes. But I thought what I'll do is I'll first talk to the main pipeline, assuming these black boxes are something called a Gibbs sampler and a Metropolis sampler and Langevin dynamics. And after I finish this, I'll come back and talk about what is involved in those boxes. Okay. So very roughly, Gibbs sampling is the following. I want to sample. Let's just look at R2. Okay, I've got a joint distribution over x comma z. X comma z, Q is my density function, and I want to generate a sample from x comma z. Suppose I have a black box that allows us to generate samples from conditional distributions. So I know how to sample from Q of x given z and Q of z given x. Then how do I sample from Q of x comma z? That's the Gibbs sampling problem. And the solution is very easy, it turns out, for this, which is looping. So you alternate between these two conditional samplers. First you start from some initial x0. Fix that x0, sample from Q of z given x0. Okay, that'll give me z1. Then fit in z1 and sample x from the other conditional distribution. You have a pair of conditional distributions, you switch between them, and eventually this will converge to x comma z, which is consistent with the joint distribution. Why does this work? We'll come back and look at the proof of this. I'm hoping I'll have about 15 minutes time or maybe halfway towards the end, and that's what I'll come to. Okay. But right now, we have this, on faith, let's all accept that this black box is available. So what's the split Gibbs idea? Okay. So I want to sample from P star of x given y. So which is P star of x times it's proportional. So I'm going to always just ignore the normalization constant. I'll just write proportionality because usually I'll take a log somewhere and hopefully that will disappear. Okay, P star of x, e to the minus this the loss function. This is what I want to sample from. Okay. So let's do the following first. It looks like it's unnecessary, but it's useful. I will introduce a new variable z, okay, and say that I want to sample not x given y, but x comma z given y, such that z equal to x. Okay. So what is the density function? Then some 1 by z, P star of x, e to the minus Ly of x times a delta function, a Dirac delta, such that it's z equal to x. So there's nothing, I haven't done anything else. I just introduced a new variable and glued it together with x. But now I can relax this hard constraint. Okay? So again, now, when I use the word I want to be careful. It's not I, somebody else. The references are here. It's just easier for me to say when I'm talking through I. Okay? This is all prior work by people. Just want to be very clear about that. Okay. Now, let's relax this hard constraint. So the hard constraint is z equals x. So what you would do is to just smooth it a little bit, put a temperature term. So instead of the delta function, it's my e to the minus 1 by rho, e to the norm of x minus z whole square. So as rho tends to 0, this will go to a delta function. But for any rho, there's some relaxation. It's basically saying x and z should be close. Okay? That's this relaxation. Let's go back to that. The first equation. I have p star of x, e to the minus Ly of x, delta function. Well, at the delta function level, I could replace x by z up there because x equal to z. So the loss function could be measured on z instead of x. Okay? But now when I relax it, what you get is a pair. So what you get is there's something which is a function of x, which you know how to sample from, the loss, which depends on z, and a third constraint that is saying x and z should be close. So what you're doing is you're breaking the requirement that you need to be simultaneously consistent with the manifold of images and the measurements. You're allowing a little bit of sloppiness between these two. That's what that rho term is essentially doing. And so now, remember in all this thing, y is one measurement. So I'll just keep y fixed. X and z are the random variables here. So the two density functions, I could write this as. So I want to sample from the joint distribution x comma z, given that way. So what is q of x given z? Well, it is some normalization, p star, so I'm pulling out the x terms, e to the minus x minus z whole square by rho. And the density function, the other density, conditional density function of z given x has the loss function as a function of z times sort of the coupling term, whereas here x is the constant, the random variable is z, there z is the constant x. So now I've got these two things, and the question, so there are several people who have groups which have sort of come to this formula up to this point. So I'm now going to talk about one particular way of implementing these things. This is by Yujia Chi and her group at CMU. I think she's moving to Yale. So that's the thing I'm going to talk about now. But there are other groups as well which sort of have come to this point and gone on different routes. So I need a sampler for this box and this box. Okay. So if you stare at this, so let's talk about the first one. This distribution can be thought of the following. So remember our original measurement tilted problem. It was p star e to the minus Ly of x. If it was a square loss, Ly of x will be a of x minus y the whole square. That means this is looking like essentially, suppose I had a measurement operator, the posterior, when the measurement was just, let's say there's some true ground truth x star. I'm just adding noise to it, and let's call that z. Then basically, this is the distribution associated with that. It's as though I had noisy observations. Okay, this is independent of what the actual loss function is. I'm just reinterpreting that particular equation as though I had noisy observations. Okay? In which case, DDPM is already set to solve it. Because if you go back to what Dheeraj talked about last week, the way you thought about DDPM is you start from the image, Gaussian noise it till you get all the way to Gaussian. That means at some point on the trajectory, you are getting Gaussian with the kind of the variance of the noise that is needed for this. So all you need to do is to reverse that process, meaning start DDPM with a particular initial condition and a particular time, run it backwards. That's going to solve problem one. Okay. So remember, I needed two samplers. The first sampler is this. The DDPM just solves this by just this observation. Okay. Now for the second one, this has no time varying term. This is some e to the minus it's a function of z, Ly of z plus z minus x the whole square. X is constant here, z is the variable. And suppose the loss function is convex, then this is just think of this is of the form e to the minus d of z. Okay, so I can just, if you have seen Langevin dynamics, this is exactly what you need for, this is what it's used, it's set up for a Langevin. And you could do other things as well. You could do Mala, which is what you would do in this case, Metropolis adjusted Langevin. If you don't know what Mala is, I'll talk about that, assuming I'll have enough time. Yeah, I think I should be able to get to it. I have till 12:30, right? Something like that. So I'll get to this and then I'll get to that. I'll talk about, so there's another black box, which is a useful sampler, Mala. You can run that and get this. So what's the pipeline we have? So you just alternate. Remember Gibbs? Gibbs is the outer loop. You sample from P of Q, X given Z, Z given X, flip flop. But for each one, I know the box. One is DDPM running backwards, the other is Mala. Go back and forth. The problem is this is expensive. So that means for getting one, so now this works, it will converge. There's no guarantee of how many iterations it'll take. There are, but with a lot of technical assumptions. In practice for real systems, these things can be super expensive because for each iteration, I need to start DDPM. So I have one, so what's the problem I was trying to solve? I give you the panda with a piece cut out and ask you to generate the whole image. So what this approach would say is, take that, run DDPM first, feed it into Mala, run that, flip back and forth, arbitrarily large number of times, each one which is expensive, eventually you're going to get this. At this scale, I would not be surprised. I don't think people have ever implemented this at this 3 million scale, but if it was, personally, I would be surprised if you can get anything to run in less than a day, okay, for these kinds of things, if at all. Okay, sorry? Nobody has ever built it at this scale, okay? So I'll show what happens. I want to go through this thinking. So I'll get to good quality samples, but I'm taking this winding road of how to think about this problem before I actually get to good samples. Okay.
I have one more question here. So in reverse diffusion, like one of the good things about reverse diffusion is that if we just do the Langevin dynamics, then the convergence rate might be very, very slow. But for reverse diffusion, it's actually bounded because the original Langevin is actually converging to Gaussian.
Correct.
So here,
that's the problem. The second one is a bad Langevin. The Mala side of it is not good. It could be fast because we're strongly convex, then we know from it'll have an LSI and then it'll be fast. But we have to go to LSI theory. Even then, it's not a single. What I'd like to do is the following, okay? As I'm doing the diffusion, at each step in the reverse diffusion, I'd like to just do one extra computation or some low dimensional computation. This is crazy. I have to run this iteration many, many, many times. That's the expense. Even if each one of these boxes are okay, overall, at least it's going to be t square, where t is the number of steps. And and usually there'll be a d dependence as well in this business. And depending on what the loss is. Remember, usually you're not interested in solving linear problems. You're interested in solving more complicated things. So in practice, that's why this is actually hard, though you're right. Yeah. So second thing you could do is importance sampling. Okay, again, we are in the test time. So I have, again, as before, an access to P star. So let's be a little bit more specific what I mean by have access to P star. Because I'm using DDPM, I have access to the following box. Starting from any xt, I have a sampler that will give me P star x0 given xt for any t. That's the box I actually have access to. Okay, as you pointed out, that's the reverse diffusion. Okay, I started at noise level t, I can get to 0. Okay. So I want to compute, I want this score. So let's do a calculation. We are going to show that this, I think I have time to go through this calculation. So let's do that. I'm going to show that this particular log conditional density can be written as the ratio of two expectations. Okay. This expectation. So it is with the random variable here is x0. So I've got some function here, G. And I want to sample from the distribution of images x0 given xt. And I want to estimate of this function. So this is something I can do. I can just do Monte Carlo. I mean, this is because I have access to that I have access to any number of calls from that distribution. I can approximate that expectation by just an empirical average, and so I can estimate the top function. Similarly, the lower one. Think of this P as just some black box. So P is used in two different ways, sometimes as a distribution, sometimes as a function. And I'm just treating this as a function with this as a random variable. Okay? And this is sampled from the same conditional distribution. So you can write the score, it turns out, as this particular ratio. And this essentially says that I can estimate the score by a large enough number of calls at each noise time step. So what the implication of this, going back to the question you have previously, is the following. I'm at a particular noise step T. I have access to the current score, but I don't have the conditional score. So what I would do is, starting from here, run many DDPMs and get a bunch of samples on the image manifold, starting from this particular point in XT. That'll give me a whole bunch of things. Once I do that, I'll estimate this function. I'll estimate the lower function. Of course, the sample complexity is likely to be bad, at least linear in D. So that's the number of calls you need, which is expensive. Yeah.
After reaching XT, you were running bunch of reverse diffusion and getting...
That's right. But now there are two things. I want to run a reverse diffusion conditioned on Y. So what I will do is, at every XT, I will run unconditional reverse diffusions, many of them, and then use those samples in this formula with the Y to get the score as a function of Y, and then go to the next step. That's the important sampling approach. You can already see this is expensive, but this is a test time unbiased sampler. I mean, this is because this is in the infinite sample limit, this is indeed correct. Of course, for many of you who know, whenever you have sort of estimates in the denominator, you're essentially in trouble. If these things are small, then things blow up, concentrations are bad, and all that stuff. Yeah, I'm not even making a concentration statement. I'm just saying in expectation, this is the ratio of these two expectations. 11:57. Okay. Sorry, I'm just trying to see if I can work through this proof, or should I do something more useful? You know what? I'll give you the notes. It's doable, but I'll take 15 minutes to do it. And I think there are more fun things to do than sort of work through this proof in this talk. Okay. If I have time in the end, I'll work through it. But take it on that. You do a calculation, you can do this. Okay. Fine. Because I really want to talk about Gibbs and Metropolis. I think if I have to do a proof, those are sort of more useful, I think, for the broader audience than this. So, okay. So on faith, then we have that this particular, you can write the conditional score as a ratio. So in principle, then so essentially this will require 2 times n times t calls for estimating that. Because at every point, you need, if I want good concentration, it says, say I need n number of samples, okay? I need it for every time step. So as I start in the reverse diffusion at some point, I get a bunch of samples. Then I step back, I get a bunch of samples. I move forward on more, each time n. So it's essentially order nt number of calls, and n may have some dimension dependence, which depends on the concentration of these kinds of things. So these are expensive. And so, yeah, you could solve this, run this on toy problems, but that's about it. So what are people doing? The real, I think, clean algorithm for, this was the first paper which actually let things scale up. Diffusion posterior sampling. Okay. This actually led to a useful algorithm that essentially allowed inverse problems at scale on diffusion models. In some sense, it allowed diffusion models to blow up in terms of applicability because of this. So let's talk about what DPS is. Okay. This is from Professor Yee's group at KAIST. This algorithm came from them. not sure. I think there are Google authors involved in it, but I'm not 100% sure. Okay. So we want PT of x given y. That's what we want. We want grad log PT of x given y. So we can use Bayes' rule as before, write as P of y given xt, PT. We know that this one is known. This is just the standard diffusion term. I mean, I'm just repeating the same thing which I just said like 15 minutes back. And this is what we need to estimate at test time. So let's write this thing a little more carefully. Okay. I want to get grad log PT of y given xt. So I'll just use total probability theorem, PT of y given xt. I'll further condition on x0, which is the clean, xt is the noisy image. I'll further condition on the clean image x0 times the conditional density of x0 given xt dx0. Okay. That's what, nothing fancy going on. But now look at PT of y given x0 and xt, this term. Well, if I know the clean image, I don't care about the noisy image because the measurement y is a function of just the clean image. So I can just drop this. Essentially, x0, yeah, this can be this is dropped, and so this is just P of y given x0. So which means now this integral I can rewrite as an expectation. So what I want, I can look at this as grad log an expectation with respect to this density function x0 given xt, which we do know how to sample from, because this we know how to sample from, because basically if I'm at time t, I have an unconditional sampler that will give me x0 of this particular function where the variable is down here. So y is fixed. The random variable with respect to which I'm averaging is actually the condition, the one I'm conditioning on. Okay. So I should just think of this as some black box function. Okay. So you could now do something unbiased by Monte Carlo and all that, but that's not what is done. Okay. Let's now do Taylor series expansion. G of x0 is this function, P of y given x0. I can expand it about its mean. Okay, so x bar is basically the conditional expectation of x0 given xt. That's the point. Gradient of g of x bar, x0 minus x bar. I'm just expanding this thing out. Okay, plus higher order terms. So what they did is ignore all higher order terms. Just do a first order approximation. Let's just do linear. But that basically means that because I'm now going to take expectation of this is a constant. I'm taking an expectation of this. This is fixed. I push the expectation inside. This is 0. So essentially, the approximation is expectation g of x0. Expectation of g of x0 approximately equal to g of expectation of x0. So something we tell our graduate students in a probability class never to do. That switch an expectation and a function. But that's effectively what is done, and it worked. It looks like images are very robust. That's basically the takeaway from this. So the next question is, okay, just because there's this expectation, how do you actually compute this x bar? Okay. Remember, I haven't solved the problem yet. I've just approximated g of x0, the grad log pt, by the following: grad log p of y given expected x0. Some conditional expectation. That's what the approximation right now is. So this has gone down. But still, it's not clear how to get this. Is there an efficient way of computing expectation? And there is. There's a very simple way. This is a conditional expectation of x0 given xt. Any conditional expectation is an MMSE estimate. It's a solution to least squares problem, right? I mean, that's what conditional expectations are. And so, but we also know the basic relation between MMSE and score. They're affine in each other. Meaning, the MMSE estimate is, if I want to ask what's the MMSE estimate at some noise level sigma of x at measurement x sigma, it's nothing but x sigma plus sigma squared times the score. This Tweedy's formula, which was derived last week by Dheeraj. Okay. Now, so he used Tweedy's formula to basically use a neural network to approximate this MMSE, and therefore learn the score. That's effectively what is done. Now we are using it in the other way. We know the score, we need an MMSE. And so you can just use the existing unconditional sampler to actually solve the conditional sampling problem, which is, so what's the algorithm at this point? I'm at some point xt. I run it unconditionally. From wherever I've gotten here because I've been guided by measurements iteratively through this algorithm. I've gotten some points. From this, I will just find some image, but then that's my average image. And then what I'm going to do is to just stick in my average image into this expression here. Okay? So this thing is going to be approximated finally by grad log P of y given expected x0. Of course, I have a gray, and then there's still an expensive thing because I'm taking gradient, and I'm going to talk about that. Okay, the expense. At least now I've got an expression. Now what I need to do is to backprop to the score network. Okay, that's really what I need to do. When I have measurements y, I need to make this consistent with that. That's what the gradient means. And next time I'll talk exactly about what I mean by that statement. Okay, but at least this is doable, and this was the first algorithm. So it was pretty good. This was a 512 by 512 scale. Today at the 1024 by 1024 square, the state of the art has moved way ahead. In particular, two problems is there are this exchange of expectation and function. Can you fix that? And two, you're taking a gradient with respect to x, which means you have to backprop through some stuff. And as score networks today are about 12 billion parameters. Okay, they're large. So backpropping through that is not an easy job. And if you want to do this like in seconds as opposed to minutes, you need to be very careful. And ideally, you'd like gradient-free ways of doing this. So can you do that? The answer is yes, and that's basically what we have developed. First, for the correction of this, you can basically look at the second order term, run a stochastic, but of course you can't do anything with Hessians. So you can run a local stochastic approximation, rank one approximation, and then iteratively run an inner loop and an outer loop. I'll show you some results with that. Then you can do procs. Instead of sort of doing gradient all the way through, you can sort of project forward and do some gradient there and essentially approximal. It's a proc algorithm, which is much cheaper in computation. And then I'm going to talk about actually gradient-free approaches. It's not zeroth order optimization at all. It's actually flow reversal. So we use sort of the connection between flow models and stochastic models, so you can do stuff. Okay? But these are the things I want to talk about tomorrow. I have about 20 minutes left. So I punted on a few things, which is what is Metropolis Hastings, what is Gibbs sampling. So I know it'll be boring to many of you, but I'm hoping that others may not have seen this, so it may be worthwhile to just talk about these blocks. And importantly, even in this era of sort of language models and big machine learning, I want to say that old classic theory is still important, it's beautiful and insightful, and actually is needed for getting things in practice. Okay? So I want to switch to that and then come back to this.
Hi, I have a small question before you do that. So you said that one challenge here is that we switch the function and the expectation.
Mm-hmm.
So one studying where this is justified is if the function concentrates very well around its expectation.
It's actually really at least the bounds are really bad. They're actually quadratic in dimension. I forget what it is, but it's something really bad, the error. So can compute the Jensen error, and it's really bad.
Yeah, but like, okay, so I get this slightly diversion, but there was this paper of Vivek and Serke from a few years ago where they looked at isoparametric distributions. And the key thing there is that so you assume that your concentration scales as e to the minus some t times L square, but there's no D in that. That's the important thing.
But if P star is not single modal, let's say it's multimodal, crazily multimodal.
Yeah, sure. So
this is what images most likely are.
Sure. So maybe there is a way to adapt this.
Maybe
for a mixture of.
I haven't thought about it. You asked a good question. I haven't thought about it, but I'm happy to chat about it offline.
Thanks.
Yeah. So yeah. So this is basically what I wanted to say about posterior sampling. Tomorrow I'll talk about the algorithms. let me just switch to sort of just classic sampling, okay? So I use these words, I showed you what Gibbs sampling is, and I use the word Metropolis Hastings. So what is the Metropolis Hastings problem? The problem is essentially the following. I have access to the unnormalized density function, okay? So there's a density pi star of x. I don't have access to it. I have function access to C pi star of x for some unknown C. Can I sample from pi star? So this started in 1950s. Metropolis, Rosenblatt, and Tellers. Yeah, so Manhattan Project fame. So they were the people who started doing this, and then Hastings sort of generalized this. So this is a really beautiful history of this thing. Yeah, let's talk about what the algorithm is. C is unknown constant. I don't know the partition function essentially. I have a density function. I don't know the partition function. So I'm going to talk about this thing in continuous state space. Similar things hold in discrete space. And I'm going to be very sloppy with derivatives and dx's and all that stuff. You can sort of clean it up yourself. Okay. So I have a state space S, typically RD. I have a transition density function, Pxy, meaning the probability of these are from X to enter B is simply nothing but the integral of Pxy over B. It's just a standard transition kernel. Or Pxy dy is the probability that if xt equal to x, it's discrete time. At xt plus 1, I'm in a small ball in y to y plus dy. That's what Pxy dy should mean. For example, in a simple thing you could think of is Pxy is just a symmetric Gaussian. Pxy is e to the minus x minus y whole square by 2, or the norm of that whole square by 2, whatever, if you're in D dimensions. Okay. I want to construct a reversible Markov process, meaning pi times pi x pxy is pi y pyx. So this is the kind of Markov process we want to construct. So let's skip this. Okay. So I want to construct a discrete time Markov process whose stationary measure is pi star, and I have access to C times pi star for some unknown C. So the idea is essentially the following. We will construct a Pxy such that pi star times Pxy, pi star x times Pxy is pi star y times Pyx. If I construct such a function, then I'm done, right? Because if you just check the stationary distribution of this, its invariant distribution is indeed pi star. Okay. So we don't know constant, but we do have access to ratios, meaning we know pi star x by pi star y for any x and y. We know this quantity because the C cancels the unknown constant. Okay. So first, if my qy given x was magically having the following property, qy given x divided by q. So this is my function. For example, it could be that Gaussian function, but whatever, it's your favorite function you've chosen. If qy given x divided by qx given y happens to be this ratio, then simply choose this equal to pxy. And then you see that by just cross multiplying, it satisfies this and you're done. Okay. It won't happen, but I'm just saying if it turns out that you're lucky enough that this happens, you're in business. Yeah, Praneeth?
It's P of y given x and P of
Did I
x
make a
given-
typo?
It's a conditional distribution, right? P of x. The pi star of x times P of y given x is equal to pi star of y times P of x given y. Maybe a typo, I think.
I'm sorry, I'm not.
In the top equation,
Oh, yeah.
and it's a conditional distribution, not joint.
Yeah. Wait, no, Pxy is not okay, bad notation. Pxy, I should correct it, is a transition. I'm using Pxy as a transition kernel,
Okay.
not as a joint distribution. I'll rewrite this, thank you. Okay, I was writing this on the plane and, okay, I'll fix it, okay. Yeah, you're right. The sort of Metropolis Hastings literature writes a kernel as xy, so I just use that notation. But we are also using it as joint. Here we are not using it as joint, we are actually using it as a conditional. Okay. Which is why this ordering here means your condition on X and going to Y. So this is really the better notation I should use, and I will do that in the correction. So in general, this is not true. So what we will do is to design an acceptance function, alpha, a function of X and Y, such that the following is true. This is a function I have, your favorite function. This times alpha xy, this times alpha yx is pi star. So if I can find a function alpha of x and y, which has the following property. When I take the q and multiply by alpha xy, and on the denominator by alpha yx, it's equal to pi star y by pi star x, then you know this is my pxy. Okay? So we are done. So I've just pushed the problem to finding an alpha which satisfies this expression. And that's very easy because if you just check it, you can just write alpha, you can take that expression and figure out what that alpha should be. It's just the minimum of 1, q of x given by q of y given x. Remember, this I have access to because this is my function I've constructed. Okay? It's a Gaussian, for example, x minus y whole square. This ratio I have. So the claim is if alpha xy is just the minimum of these two, you stick it in, you're going to see that it satisfies that. So what is the algorithm then? I want to sample from the distribution. This is my transition probability, P from X to Y. I'm just writing it this way so that there's no confusion. So how will I do that? So first, I will generate a Y from Q of dot given X. I can sample that because I have access to this function Q Y given X. I'll generate a random variable U uniform 0 to 1 and compute alpha xy as follows. If U is less than alpha of x, y, switch from x to y, else don't do anything. So this is why this is an acceptor. And why is this the accepting? Because of the following reason. Let's look at the random variable A is the indicator that U is less than or equal to alpha xy. Okay, then the density function then let's work through this. I want to figure out P of xy dy. That is the probability that the next step I'm between y and y plus dy given my current state, which is I'll further condition that I accept and y is approximately equal to y. It can be cleaned up. Okay. I'm further conditioning on this times the probability A equal to 1 given these two times probability y approximately equal to y given x. I've just written it out. Look at this term. This term, the probability that you accept, now here I've told you I've accepted y equal to y and xt is x. Therefore, by definition, xt plus 1 should be y. So this must be 1. On the other side, when I do total probability, a equal to 1 and a equal to 0, when I do a equal to 0, this part goes to 0. So essentially, what I'm going to get is pxy dy is the probability I accept times the density dy. And the probability I accept is essentially u is less than or equal to this, alpha xy. And because it's a uniform random variable, this probability is exactly equal to alpha xy. So that's basically the proof of Metropolis. Now, what's Gibbs sampling? Gibbs sampling is a special case of Metropolis Hastings sampling where you always accept. And the idea is essentially the following. Suppose I want to sample from a joint distribution pi star x1, x2 up to xd. Okay, this is what I want to sample from. So what do I do? Well, I can write pi star of the x1 through xd as pi star of xi, condition everything but I, times pi star of the rest, okay, for each I. And so I do the following. I start from I look at this vector x1 through xd and pick a random coordinate. We could use any distribution. Let R of b be the distribution of the random coordinate. And what you do is you assume you have access to the conditional samplers, which is what the Gibbs sampler assumption is. If I have access to the conditional samplers, I'll pick a random coordinate, condition on all other coordinates, and sample that one random coordinate. Okay. And now stick it in and then iterate. So this is Gibbs sampling. We will see that if you if this is the dynamic you're doing, okay, and you work through the calculations, since I'm sort of running out of time, I'll let you read to yourself. Essentially, it turns out for this, it's a Metropolis Hastings system with alpha equal to 1. So you can reduce it to that. And therefore, what we talked about originally as Gibbs sampler was essentially a special case of this, where there's just 2 elements. Okay, you can generalize this to D elements. So this is classic sort of sampling. And now what we have is a way to suppose you have conditional samplers. You can sample from conditional distributions, then you can sample from the joint by iterating. Now, stepping back, I mentioned 2 things earlier. Remember Gibbs and Mala. So Mala is essentially the following. So you know the Langevin dynamics. I'll use Langevin dynamics as my Q, my proposal, and run Metropolis algorithm on top of it to accept or reject. Okay, that's Metropolis adjusted Langevin. That's sort of the box. And Gibbs box is now clear. So I think I don't want to get into any more details of the proofs. I think I'll sort of stop at this point. Thank you.
You told us about Metropolis Hastings, which was about generating samples from PyStar.
How did it come?
Because you told us about Gibbs, which is okay, conditionally we can sample, but we want to do from joint.
How did they come together? So let me repeat. Yeah. Sorry, I was too. Remember the split Gibbs? If you want to do exact sampling, what you needed to do was split Gibbs. So you need a Gibbs between X and Z. So that's the Gibbs. Then inside the split Gibbs, there are 2 pieces. One was sampling consistent, the conditional first conditional sampler is just consistent with sort of the measure, with the P star. Okay, that was the reverse DDPM flow starting from a particular time. The second, the exponent was something to do just with the measurement loss. That could have been done using a Langevin itself, but you can speed this up further through Mala, meaning you use a 1 step of Langevin and then use that as a proposal distributions or running it all the way and run Metropolis and see whether you accept or reject. So that is the Mala algorithm. So you iterate, these 2 boxes fit into that. And when you iterate that loop, you're going to get posterior sampling. And that is probably correct as opposed to an approximation. So the problem with that was it doesn't scale, but at smaller scales, that will work. Okay. So that's how that comes together. So next time I talked about a first order approximation, right? I'll talk about higher order approximations, other types of algorithms, how does text come in, the guide. There's a lot that I sort of brushed under the carpet here. I'll talk about real constraints, and I also want to spend some time talking about rectified flow, because today's state of algorithms like Flux or even SD 3.5 are all RF flow algorithms. So how do you adapt samplers? What does sampling mean in the flow world? We'll talk about that tomorrow.
Just a very quick question. So in this Metropolis sampling, when we want to sample from PyStar, what's a good queue? Do we have good insights on that? Or are you using some? Yeah.
That's a whole community in itself. I just made up one queue, which is, this is a standard queue, which is symmetric, but it doesn't need to be symmetric. In fact, the original Metropolis algorithm required qx given y should be equal to q given y given x. Hastings was a person who allowed this generalization.
There's no kind of one-line wisdom.
There might be, I'm not the right person to give you that.
No, I'm just a chair. I don't have a question.
So I do not fully understand how Metropolis adjustment speeds up Langevin dynamics, because Langevin dynamics, if we run it, it will also converge to the target distribution. Mm-hmm. So how does the adjustment step actually speed up the convergence? In what scenarios?
I'll give you the statement I've read, okay, because that's, I don't have a proof. You want to say? Okay. But you could do LMC. You could do Langevin Monte Carlo. You could do discretized. You could do discretize the Langevin using Euler-Mariama, right? That you could
right,
discretize.
But that will not sample. But that will be biased, right? There is paper who is the name Arnak Dadayan. He wrote papers in which.
Right. Exactly.
Yeah. So you adjust. You add the Metropolis.
Zero bias.
With adjustment, it will be zero bias. So what I think people do is just one step and then use that as a proposal and then, yeah.
Yeah, I think like the assessment step, general.
But you'll reject a lot of samples. The expensive thing is that a lot of you'll not make much progress, which is why this is sort of the beginning to go to HMC. For people, I mean, you could go off on that direction, but I don't understand that very well, to be honest. Okay,
Any other question? Okay, doesn't look like so. Let's thank Sanjay again.